Alright, so what have I been doing at the Gecko Music Studio Lab? Well, I've been working on a way to test capacitors, to determine capacitor values using a sound card. I apply white noise to the capacitors and then measure the frequency response of them with a basic RC filter. So you can see the response here. It's flat in the pass band and has some slope in the stop band there. What I've got here on the input of the sound card comes in, goes in series through the capacitor and then into a resistive load here that goes to the sound card. What I do is I apply that white noise, I take that spectrum, paste it into this spreadsheet here that I made, and based on the load resistance, either 150K, which is the Jam Labs internal impedance, or 10 kilo ohm resistor, 1 kilo ohm resistor, or 100 ohm resistor, these are the capacitor values that would be calculated based on knowing the frequency, and that's assuming the 3 dB point. So once that's pasted in there, it calculates the dBc from the baseline, which would be just applying white noise and measuring that directly. There's a couple things I look for here. One is where that 3 dB point occurs. That you can see is right about here. The second thing that happens at the 3 dB point is that the slope changes to about 10 dB per decade, and that's indicated here. You can see that that transition is right here. So that means my capacitor value, right now I have a 1 kilo ohm resistor, so I'm going to use this column, is about 100,000 puff, or 0.1 microfarads. This one actually has markings. It says 104, which would be 10 times 10 to the 4. So that's pretty close. It did calculate the value. Now, some capacitors have a lot of effective series resistance, which is essentially loss in the pass band. It stays resistive even at high frequencies, which are in the pass band of the RC filter. For example, this capacitor here, you'll notice that this flattens out right about here. Now, if I put in this other capacitor, which has a very poor or very high effective series resistance, this will drop down significantly. See, it's way down there. It's dropped about 10 dB, and that makes the 3 dB point off. So that's calculated, that passband loss is what I'm calling that. It's calculated based on the high frequencies. I take the 10 high frequency points and average those and call that the passband loss. So then I add that back into the dBc when I calculate that, and that gives me a better 3 dB point when I'm looking at the dBc as opposed to the slope. Okay, and that just hit my 1,000 samples there. I'm going to copy this data, paste it in to my measurements here, and look at my dBc, where that crosses 3 dB is about here, and you'll notice that also the crossing of the 10 dB per decade is just about here. There's quite a bit of noise on this, but it looks like my value for my capacitor would be in this range. It's between 170 puff and about 190. So that's pretty close. This gives me range from 50 puff and all the way up to about 40 microfarads with a 100 ohm resistor. So that's it. That's what I've been working on.